Welcome back to Contemporary Math for one more video on apportionment methods. We want to look at Webster's method for apportionment in this video. So Webster's method asks us to again find a modified divisor where the divisor is such that when we round to the nearest integer on the modified quotas, okay, so we find a modified divisor, divide the group population by the modified divisor to find the modified quota. Take the modified quota and round it to the nearest integer. Once we round it to the nearest integer, add all of those modified rounded quotas, add all those up, and that should be the exact number of things to be allocated or to be apportioned. So it's essentially the same thing as we did in the previous problem, just the rounding is different. Instead of always rounding down, we're rounding to the nearest. So we just want to choose appropriately, find the appropriate modified divisor to have everything distributed appropriately. So again, first, notice that the standard divisor is 12. We calculated that a couple times before, so I don't think that we need to discuss that much. But what I'd like to do then is I would like to remember, right? Remember a couple of things here. We are allocating or apportioning 200 nurses, and maybe a good idea to remember how many calls are in each group and each shift, that is. So we want to find a modified divisor. We need shift A, shift B, shift C, and shift D. All right, and then in each of those shifts, there are 751 calls in shift A, 980 calls in shift B, 503 calls in shift C, and 166 calls in shift D. And of course, again, we're looking for a total of 200 nurses, so we want to make note of what the totals are in each case. So we create ourselves a table again. So we'll take a moment to do that. When we write up our apportionments in each case as we try them, it is not necessary for us to write the unrounded version. If you choose to write down the unrounded version, that's fantastic. So in the previous example, or in the previous method that was shown, we calculated the modified quota and then we rounded it. And showing this allows us to recognize, hey, we took this number and we rounded it to that, which is helpful. Okay, that's very good. But is it necessary for you to show this number here? No, it's not necessary. If you just give the rounded number, that would be okay. Of course, if you round incorrectly, it's hard to identify that. And so you may end up losing some points if things are rounded incorrectly, but that's okay. You know, not showing it is okay if you do all your rounding correctly. Let's see. So I still want to add a few more of the lines here. And you may want to just add these as you need them, and that would be okay too. All right, so we start off with our standard divisor, so that way we know how we need to adjust these things. So again, we would calculate them to be 62.58, 81.66, let's see, 41.992 rounding to 2 decimal places, and 13.83. So here in Webster's method, what we're interested in doing is rounding to the nearest integer. So having a decimal place of 0.58, we would round up. So that would be 63. Having a decimal place of 66, we would round up to 82. Having a decimal place of 92, we would round up to 42. And having a decimal place of 0.83, we would round up to 14. When we do that, let's see here. It looks like I got this to be 201. Let me double check that. Let's see here. We can double check that by saying 63. I'll make sure our calculator is turned on first. It doesn't want to wake up for us. File, wake up, new. Hey, let's go ahead and use that one. So let's clear that out. And we have 63 plus 82 plus 42 plus 14 is equal to 201. Okay, excellent. So it is what I said it was in my notes, 201. Perfect. But this isn't perfect overall because that's too many nurses. So this is too big. And what that tells us is we need to increase the divisor. So we need to increase our standard divisor to a modified divisor. And in the last example that we looked at, a very small change worked out to be perfect. So let's go ahead and try a really small change. So 12.1, because last time 11.9 worked. So we're going to try 12.1, just changing by 1/10. And when we do that, when we take 751 divided by 12.1, we get 62.066. Awesome. 980 divided by 12.1 is 80.99. 503 divided by 12.1 gives us 41.57. And 166 divided by 12.1 is 13.71. So we calculated what those modified quotas are, and we just need to round them to the nearest to find the rounded quotas. So with this decimal place, we would choose to round down to 62. With this decimal place, we would choose to round up to 81. With this decimal place, we would choose to round up to 42. And with this one, we would choose to round up to 14. Now what happens here is I had too many distributed, and so I decided to increase the divisor to decrease my disbursement. But I decreased by 1 here, and I decreased by 1 here. So I would actually find that I would need to, or that's going to give me 199, right? So I decreased by 2 instead of decreasing by 1. So 1/10 was perfect in our first example, but it was not perfect in this one. So what we find is that this is too small, right? 199 is too small, so we need to decrease the divisor. Okay, so we decrease our divisor to 12 point, right? So when I find that I went from being too big to being too small, I'm just going to split the difference and see if that works out nicely. So let's split the difference, 12.05. When I do that, I end up with 62.323, 81.327, 41.74, and 13.77. Rounding to the nearest integer gives us 62, 81, 42, and 14. So I actually didn't decrease it enough. I still have 199. The number I found is still too small. So I will decrease the value of D. Now again, it was still too small. So I'm going to take the difference between what I have this time and what I knew was too big, hoping that that will again be the correction. So 12 point, halfway between this and that is 0.25. Right, so I'm very, very small, right? Very, very small difference here. So when I do that, I find that this is 62.45. This is 81.58. This is 41.83. And this is 13.80. So this works out very nicely because this still rounds down to 62, but this now rounds up to 81. So I am able to increase the number of nurses distributed. This still rounds up to 42. This still rounds up to 14. And I have this rounds up, and I still wrote 81 there. This rounds up to 82. So I have one additional nurse distributed, giving me the desired distribution of 200 nurses. So this is perfect. With that, the apportionment is, let's see here, shift A, we said receives 62 nurses. Shift B receives 82 nurses. Shift C receives 42 nurses. And Shift D receives 14 nurses. And this works out, that's the 200 nurses we needed to distribute. So that is Webster's method. And I'd just like to finish this video off by reminding us of Adam's method, or sharing Adam's method. So for Adam's method, what we do is we find, again, a modified divisor, but we find one so that way when we round up, we get the desired distribution. So here we rounded to the nearest. All we would need to do for our last method, Adam's method, is we would need to round up. So in this case, if we were to round up, it would be 63. Actually, this is exactly what we would have, right? So this is fantastic. And then if you pay attention closely to what happens at 12.1, you might find that that's about all that we need. Okay, if we always round up, we distribute too many. So we need to have a little bit less when we round up. Okay, so if you pay close attention to what we've done here, then you find that there's a little guesswork into what happens in this procedure. So take a look at this. If you have any questions, make sure to ask during lecture, and I will see you guys again soon. Okay, because we still have a few classes, so I will see you guys during the lectures that we have left. Have a great day.